So we were talking about Chapter 10, getting started on it, which covers the planets Venus and Mars, both terrestrial planets. What is our chapter plan? It is to discuss Venus first. We are going to cover the surface, the atmosphere, and I left the slides in, but I am skipping over exploration, and you are not responsible for it. The slides are just there for your own interest if that is something you're interested in. Then we will move on to Mars, which is going in the direction as we away from the sun and to the outer solar system. And of course, skipping over Earth, which orbits in between these two planets. And as far as Mars goes, we will cover its surface, the atmosphere of Mars, its moons, which are very exciting, mostly because we haven't talked about any other moons except ours. So, hey, turns out there's other moons in the solar system. Surprise, surprise. And just as with Venus, I will not be covering exploration, nor are you responsible for it. All right, so let's do a summary of sizes that we've seen so far. Sorry for this strange font issue with some of the words, right? That's what happened to Venus, the word Venus, that is. Okay. Here we have scaled images of Mercury, the Moon, Venus, and Mars. And if we have a consideration of Earth, which of these is correct? Is Earth sized as shown in number one, number two, three, or four? What do you think? Let me know your answer. And it'd be on the same scale. You all know that, right? Yep. Okay. Well, thank you, Ace, Isabel, Patrice, Angelina, and Anthony, for putting in your answer. You all agreed that it would be number two, which is a little bit bigger than Mars, right? Because we can easily see, kind of, if we put overlap Mars, but significantly smaller than Venus. However, it's not. It's number three. I don't know if number three just looked too big. Maybe it just kind of jumped out at you as looking a little too big, but no, Earth is almost exactly the same size, so the same diameter as Venus. And it's much larger than Mars. Okay? So it's the diameter of Earth is not quite twice, but almost twice that of Mars. Yeah, it's kind of funny, right? It was almost like an optical illusion that it looked too big. Though I even had like a moment where I was like, "Whoa, three looks really big." But then I remembered, well, it's the same. I know the Earth is the same size as Venus, and I looked at it and I said, "Oh, well, yeah, But that's that sort of, visual cue issue, right? That it just looked too big. But you do all see, I'm sure, that it's the same size as Venus if with this image, which is accurate. They're remarkably close in size. All right. Yep. Well, now you know. Probably memorable. So here they all are together to scale. Mercury, Venus, Earth, Mars, and Moon. And as far as the Venus and Earth being so similar in size, Earth is the slightly larger one. Yep. Yeah. That was key for me. And that's the fact that like that helped me, and recognize it. It's like, okay. Just remember Earth and Venus. They're like twins. But Venus is the evil twin. It's actually that's it's sometimes described that way. Not because Venus is an evil planet, or let alone the mythology of, the god Venus is evil in any way. It's just that it's such a hostile world in terms of the surface being impossible to live on, which we'll talk about why. And so that's why it's like, okay, well, you can't, since you wouldn't survive for a minute on Venus, that makes it seem like kind of an evil place, at least a hostile place. So, which of the following, moving on, is not a way that Venus resembles Earth? Just, relevant to our discussion. Germane to my ramblings. So you got all of them are, right except for one. Although, if you think that none of them are right, you could choose five and say, no, actually, Venus is matches all of these criteria: size, density, surface gravity, and atmospheric thickness. Anybody else? We got one answer so far. Cool, cool. Okay, a couple more. Yeah. And Patrice, I guess you didn't second guess yourself this time because you got it right. So Venus definitely same size. We just saw that. It does have the same density, so the interior must be pretty similar, made out of similar mixes of rock, heavy metals, and so on. And actually knowing that if one and two are true, three has to be true. Because if you remember the universal law of gravitation, the value of gravity comes from distance and mass. And the distance in this case is the radius, and the mass is the mass of the whole planet. And so, since those two values are quite similar, so is gravity. If you went to Venus, you would weigh as much as you do on Earth. Whereas if you went to the moon, I like your enthusiasm. But if you went to the moon, then you would weigh about 1/6 as much as you weigh on Earth. And if you went to Mars, you'd weigh not a half, but like 4/7 as much as you weigh on Earth. And exactly, the thickness and pressure of the atmosphere is oppressive on Venus. The atmosphere is a killing atmosphere. It's incredibly thick and incredibly high pressure. So before we get to that, which is probably where we'll leave off when we get to the atmosphere, let's talk about the surface a little bit. Of course, we have to describe the characteristics, which we've definitely hinted at. So let's just make sure they all match, right? So here is our size, 81% the mass, all right? So it is a little bit less dense because the size is much closer. So, the radius is 95% the radius of Earth. So Venus's radius is 95% of Earth's. But the mass, is lower. So there's obviously some lower density material, but that's not surprising because remember, Earth is the densest of the terrestrial planets, and probably because it lost, a lot of its mantle to make the moon. Not that like it willingly gave it up, so how that sounds like when I say it that way. But anyway, so this is the density, and the density for Earth was above 5.5. So that you can see that in the decimal places, you got that lower density. But they're both above 5 grams. But there is a difference in that 10th of a gram per cubic centimeter place. The orbital period. This is a so we just finished talking about the weird orbit of uh, you know the Mercury. I don't know why the word wasn't coming to me. And I find it super fascinating. I love that whole maybe just because like it took me a while to think about it, so once I got it, I was like, oh, it's cool the way the two-thirds resonance works. So I totally get that it isn't an easy idea to initially wrap your head around, but it does pay off, and it's kind of cool once it makes sense. But Venus also has a unusual relationship with its rotation and its revolution. In other words, its day and year. And what the way that works out is okay, so we have an orbital period, 224.7 days, and the rotation of the planet is about the same. So it takes just as long for it to rotate around its axis as it does for it to orbit around the sun. Okay, that I'll come back to that. The semi-major axis is 0.72 AU. This is just telling us how far it is from the sun. So it's closer, right? That means it's going to be hotter. The sunlight's more intense, right? So even if it wasn't for the oppressively dense atmosphere that completely encases the planet, it would be a pretty hot planet just because of how far it is from the sun. But check this out. Here's its rotation period, negative 243 days. So I just said that these two values are about the same. And they are in terms of their magnitude or their absolute value. But the rotation period is negative. What does that mean? Right? Does that mean that the rotation is going backwards in time? If you go to Venus, do you like, do you like start to become younger? Is it time travel? I can only assume that that's what it means. Well, although that's interesting and fanciful, obviously not the case. The rotation period being negative means it rotates the other way. So everything in the solar system we've talked about rotates counterclockwise. But it's the everything, except there are, as the adage goes, the exceptions that prove the rule. And people hate that expression, but I guess that kind of makes sense because if you have a rule and acknowledge no rule is perfect, then the fact that there is an exception and you call it an exception, which implies it's rare, well, that means that the rule is at least valid most of the time. So this is the exception that proves the rule because Venus doesn't rotate in the counterclockwise direction. It still orbits in the counterclockwise direction because that is universal. There is not a planet that orbits the other way. All right. But it does rotate what's called a retrograde direction. Because prograde is counterclockwise, retrograde, the other way from everything else, is called, is what was clockwise. Okay. And you can see it with the little arrow here. And that means effectively that the planet is upside down. So we refer to its axial tilt as 177 degrees. And that's pretty close to 180. And that's where this retrograde rotation comes from. By just thinking about you had, a spinning planet that was spinning counterclockwise, and then you turned it upside down. Well, now it appears to be, and effectively is spinning the other way because you've turned it upside down. All right. So whether you think of it as, rotating clockwise or being tilted 180 degrees, the result is the same. The last thing that ties this all together, and that I'll say, because obviously I'm talking about this for a long time, is that the combination of these two make the orbit unusual. And what I mean by that is that if it wasn't for the axial tilt, if these two numbers, 243 and 224.7, were the whole story, then we would just say that Venus is tidally locked to the sun, because it would be. It would have a rotation period and an orbital period that are, really close to each other. And that just means it would always have one face that faces the sun. And it'd be kind of easy to talk about, what a day is because there wouldn't be one. There'd be one half of the planet that's just always faces the sun and one half that doesn't. And that would just be exactly like the relationship between the moon and Earth, which is probably the biggest reason that I kind of am saying that it would be more intuitive because we already know about that type of orbit. It's exactly what the moon does around Earth. But Venus is upside down, which means that it's spinning the other way, and it does still experience day-night cycles. So I'll leave it up to you, and we can talk about it another time about what it looks like. Because it results in a very strange relationship between the solar day and the sidereal day. But there is a day-night cycle because of the opposing direction of the rotation to the orbit. All right. So, how is Venus like Mercury and the Moon? Well, it's got some of these, key characteristics like big lava plains, like the Maria on the Moon. It's got highlands that are heavily cratered, and it's just got lots of craters. Okay? So, compared to Mercury or the Moon, what do you think? Does Venus's surface have more craters or fewer craters? And you have to go off some pretty limited information here or something that you have known by, reading ahead or whatever. But just think about what we've been talking about some of its conditions. So let me just get a couple of best guesses here. Okay. Fewer. Okay. Okay. Patrice and Isabel say fewer. And you're absolutely right. And I would venture to say you were thinking the atmosphere, right? That having such a thick atmosphere means that fewer things can get through, right? You've got fewer craters because more asteroids are burning up when they pass through that atmosphere. And that's basically what's going on, right? So you've got a significant amount of craters because there's not much resurfacing, so there's no way to erase them, but there is a way to stop them in the first place. And the thicker atmosphere, although not a perfect protection against asteroids, and nor was it in the past where there was even more of them in the earlier solar system, it does reduce the number. And in particular, the smaller craters, because the craters that would make, or rather the asteroids that would make those smaller craters, are the ones that completely burn up. So you got a cutoff, right? Because any size rock can make it to the surface of Mars. Well, not the surface of the moon, right? In particular, Mars also to some extent, but certainly the moon, but not so with Venus. They'll melt. All that air resistance, all that friction, they will burn up in that atmosphere. I mean, they burn up in our atmosphere, and ours is not as thick. And the larger craters are often multiple or asymmetric, which kind of goes against the kind of the prevailing logic about that symmetry created by the explosion. And the largest crater, which is Meade, that's the name of the crater, so it's the Meade crater, is slightly larger than the Chicxulub crater. This is the one which is associated with the impact event that caused the extinction of the dinosaurs some 65 million years ago here on Earth, and their sizes, Meade and Chicxulub, comparably, are around 93 miles wide. Don't ask me why they didn't use kilometers. All right. And so, right, what does this tell us about the surface? It actually, so, okay, I said there's no resurfacing. I should, especially, with this question, give some explanation of that. There's no ongoing, or at least very little, ongoing resurfacing. There's not, plate tectonics, and there's not a lot of weather that's scouring the surface of the planet, despite having an atmosphere. There's not high winds, or there's no precipitation. There's no cycle of liquid being rained down on the surface. But despite that lack of erasure, there appears to have been, in a way that I've seen this described, some earlier resurfacing events. So we're talking the first billion years of Venus's history. There was some major lava that covered a lot of that primordial surface that still is visible on both Mercury and the Moon. So so we have Venus, right? So more than 4 billion years of history, and then actually even more. They're talking about even more recent resurfacing, but going back to 3 to 600 million. So a much longer time frame than we saw for the oldest visible craters on Earth. Those don't go back more than 100 million. That's like the absolute oldest possible evidence you can find. Whereas you can get, 6 times that on Venus. And again, as far as I know, it's particular events rather than an ongoing process. as is the key explanation of the resurfacing. So some major past volcanic events. Okay, now and the moon, right? You have 4.1 to 4.3 billion years of cratering history. That's what all this is referring to on the moon, and then the Maria are were covered up, around 3.3 billion years ago, and then started getting recratered since then. There's this kind of like this topic that we won't talk about for another couple of chapters that keeps coming up about why there's kind of this big variation in cratering. Um, I just want to warn you about that. It doesn't matter for now. You won't like need to know it for getting score on a test or anything. But there's if it feels like there's some like surprisingly big difference in the number of craters, there's a reason for it. And it just has to do with like there was I already kind of said it, paraphrased it a second ago. There was a lot more cratering going on in the very early solar system, which might even seem intuitive, right? Because there was a bunch of more leftovers back then, and it's a real drastic difference. And that's so when we talk about like you know being able to show a certain number of years, billions of years of cratering history, it makes a big difference between being able to show this period that included 4 billion years ago and a period that included a striking amount of history up to over 3 billion years ago, but crucially didn't extend back to that 4 billion mark, right? So the moon is a great demonstration of that difference. Venus isn't, right? Because Venus only has a few hundred million years of cratering history. Here is the surface of Venus shown with colored elevations. So we can see kind of what look like continents. I've always thought that the surface of Venus looks like it has like these big continents and what could be like an ocean bed, but of course there's no ocean, there's no liquid on the surface. It's all dried up, right? It's just a totally barren surface, but very noticeable highlands, almost like continental sheets, continental plates, and then a much lower region, which is the lava plain region. And there, there's no, yeah, they look like continents. And I know I've read various things about, could there have been some plate tectonics? Is there any direct evidence of it? And I think the jury's out on that. Whether there's certainly not any now. There's no way that there's active plate tectonics, no sliding around, no subduction going on Venus. And as we briefly touched on, it's a big part of that is that the complete lack of oceans doesn't create kind of the key movement mechanism of having those weighted down higher density plates, which are the oceanic plates, that then can slide into the continental ones and kind of like keep the whole process going. And whether or not that's the absolute key to plate tectonics or not, it's certainly lacking on Venus, and so are the plate tectonics themselves. Now, talking about kind of contemporary research is actually, I remember when this was first in the science news. I say the news, but it's really just the particular news outlets that pick up science news, was that there has been some pretty, confirmed evidence of continued volcanism on Venus. And you might think, oh, sure, yeah, Venus has volcanoes, big deal. But it would did when I first learned about Venus in school, I learned that it didn't. So this is a recent change in our understanding of basically, some big ideas about how much heat is still left in the interior, about, whether it can, what the crust looks like and how that heat can get up through the crust. But point being is that there appear to be volcanoes still erupting on the surface. And by showing that there is some, it might suggest there's a lot because it's not easy to see the surface of Venus because that atmosphere is so thick. The good observations, high resolution ones, are very difficult because only radio waves get through the atmosphere, and radio waves inherently are low resolution because of their long wavelength. So there could be easily a lot that we're missing. Even on a flyby mission, if we fly a probe nearby Venus, it doesn't improve the resolution much because we can't get visible light through the atmosphere. It's just totally opaque to visible light, infrared, even most microwaves. Okay. So on Earth, volcanoes tend to follow fault lines. On Venus, since there are no plates, volcanoes are evenly distributed around the surface. Now, and until recently, these were all thought to be dead volcanoes. Now, that said, there's a lot of them. There's a lot of volcanoes on Venus. It was just, like I said, the conventional knowledge, the conventional logic that they were all dead volcanoes, and most of them probably are. But a few of them seem, well, at least one seems to still be actively creating lava flows. And again, that might just be the tip of the iceberg. Maybe many more of them are active than we thought. Mhm. Ah, I don't know why I panicked. All right. So I already mentioned tectonic activity. So this is this idea here, the ridges and cracks. It is the best support of the theory that there was some amount of movement of plates, so a, a crust of the planet that was driven by a hot mantle and with a lubrication level at the top of it, which is actually a liquid part of the mantle, right? Although we talk about the mantle being solid, it's got a kind of a thin liquid effect, and the plates moving around and scraping against each other, sliding around, and that's this buckling, stretching, compressing of lava, and no other kind of good explanation of where that could have come from. No like prevailing theory that Venus changed size in the way that Mercury did. Although we that was in the material that I told you to look up on your own. Mercury does show like direct evidence of shrinking at some point, and there's these big leftover cliffs that show that, but no such on Venus. So probably plate tectonics at some point, but not recently. Now, the volcanoes on Venus tend to take strange shapes that don't look like Earth volcanoes, nor do they look like Martian volcanoes, which actually look more like Earth volcanoes but tend to be larger. Instead, the volcanic activity on Venus, which is under the heading tectonic activity, because maybe they would have been, you know, driven by some sort of tectonics, but not major plates though, because of the distribution of volcanoes rules that out, right? So at least it would have been just like little fault lines, and so more like a spider work of fault lines rather than a spider web network of fault lines rather than major plates. But all these volcanoes all over the surface. So some of them have a name where they are called coronae. And the coronae, not to be confused with coronae from the sun, unfortunately, the word gets used for both. And we'll talk about that when we talk about the sun and the surface of the sun. But coronae on Venus actually refer to these lava flows. You call them volcanoes, but they're almost like they're not. They're just like bubbles. They're crown-shaped concentric cracks from rising and receding lava. So it's just like lava just bubbled up from underneath the surface. Didn't make a volcano where there was like a magma chamber and like kind of a particular release point, but just kind of just pushed up through the surface. And we see it again with these big lava domes, these pancake-shaped, wrinkled and cracked rock on the crust from rising and receding lava. So it's just like the crust just completely gave way and the lava was able just to push through in volume. And so that's just think about these, not tall volcanoes, but instead just big bubbles and flat deformations of lava flow. Okay, and let's get through a little bit of the atmosphere, since supposedly it's so interesting, right? Killer atmosphere. Remember this primary atmosphere? This is the same one that we started with. And this is a cool idea, right? That we can use this argument for all of the terrestrial planets, actually all the planets. That all the planets would have started with the same available gases, the gases of the protoplanetary disk, right? And that they were hydrogen and helium, right? Formed from gases around the sun. And we already know, do they have large or small masses? Small, right? This is literally the same slides because it applies to Venus just like it applied to Earth. And they probably repeated them in case you want to do them in a different order. Okay. Now, What does the modern atmosphere of Venus look like? Well, as you can guess, is not hydrogen and helium. Those would have escaped into space for the exact same reasons that hydrogen and helium escaped into space from Earth's primary atmosphere. Today, there are sulfuric acid clouds, so about 20 kilometers of sulfuric acid clouds above a 30-kilometer thick troposphere. So overall, it's a pretty low elevation atmosphere because notice that it only totals about 50 kilometers. That's in comparison to ours, which is a healthy 100 kilometers. And I say healthy not in the comparison sense to the killer one, um, although probably a poor choice of words. It just in the sense of like that's like a lower limit. Our atmosphere really, like if you when you look up how high does the atmosphere go, you often see 150 as a good estimate. The reason there's not like one defined number is it just gets gradually thinner, and it even varies depending on the strength of solar storms pretty significantly. But somewhere in that 100 to 150 kilometer range is the height of Earth's atmosphere. Venus is only 50. The pressure is 88 times more than Earth's, and that's the pressure at the surface. So 88 times the pressure. All right. So that's equivalent to so yeah, okay, so that's equivalent to 30 feet underwater, and it's two times more than at that's at so 88 times more than Earth's. Oh, right. 30 feet underwater, two times more than at the surface. Um, two times more. Because I always hear it as approximately as around 100. I'm trying to make sense of the sentence. So eight, 8 times more than Earth's. Yeah, okay. So it's comparing Venus's atmosphere and it's saying, hey, this is how pressurized it is compared to going 30 feet underwater. So it's 88 times more pressure than being on Earth 30 feet underwater. But then the second part, two times more than at surface. Well, I might have to circle back around to see what I'm trying to make sense of what they're saying there. Unless they're saying this is the pressure at 20 kilometers, and I'd just look up and give you the number, but I don't want to, spend the time. And I remember, reading in the book just recently, that it's like a sentence that was just sort of saying in the passing. It's like, Venus has, around 100 times the pressure. So that's kind of the rule of thumb that is the top of my mind. So we'll have to stick a pin in it for now, okay? And we'll come back to it. But this, at least this first part of the sentence before the colon, is a good way to think about it. So if you swam 30 feet underwater, where your ears would hurt quite significantly, right? That's pretty deep. And then you multiplied that pressure by 88, you would get the pressure on Venus. Okay, surface temperature. So it's the hottest planet in the solar system. It has the hottest surface. And because we don't talk about the gas giants having surfaces, so rule them out, okay? But of the terrestrial planets, it has the hottest surface temperature by far, way hotter than Mercury, even though it's not nearly as close to the sun. Mercury, by the way, if we were comparing superlatives here, Mercury has the greatest change in temperature because it's got that swing from 400, positive 400 degrees Celsius to about negative 400 degrees Celsius. So it has the greatest swing in temperature. But Venus by far has the highest high, and it doesn't vary. That temperature, that 750 Kelvin surface temperature, just doesn't change. I mean, on the one hand, as we talked about, the Venus day is incredibly long, right? Hundreds of Earth days long. So you might expect the change to be really gradual anyway, but it's just non-existent. That the surface temperature is completely independent of what side of the planet is facing the sun. The atmosphere is just so thick and it's holding in that heat at the surface. And so it just there's still an energy flux with the sun, obviously, energy in, energy out, but that that doesn't affect the maintained temperature on the surface underneath that thick blanket of atmosphere. It just sits at 750 Kelvin. And you could compare that to like the way that an interior temperature inside a planet just gets maintained, right? It just sits at a particular value. Same going on here on Venus. There are uniformly hot, dry, and only gentle winds, so no major weather events. Also, like I said, no rain of any type. Obviously, it wouldn't be liquid water rain, not at that temperature, right? But nothing, no liquids raining down, right? Hot, dry, and gentle doesn't sound so bad, right? But then when you realize that it's hot, dry, and gentle at 750K, you realize, what conditions you're talking about. And although we won't cover the exploration aspect for either Venus or Mars, this image is taken by a lander that landed on the surface of Venus. But none of the landers that have landed and taken photos last very long. They only last for a few minutes before their, circuitry, the whole device fails and no more signals are received. So there's only a few pictures, and I think it kind of indicative of that difficulty of keeping a electronic device working for any period of time on the surface of Venus is shown in the fact that this famous picture, one of the few pictures taken of the surface of Venus, is kind of looking straight down, right? We don't even have a good horizon view because the you know the robotic arm didn't even work in order to move the camera up, so this was the only picture that could be taken before everything died. So the current atmosphere, oh, sorry, well, not current. So let's run through secondary. So secondary, we had a breakdown. So the primary and secondary atmosphere of Venus, Mars, and Earth were pretty much the same. So when we talk about secondary atmosphere, uh, if you remember, I explained a lot of the explanation of explain the explanation, but I talked about where these different components of the secondary atmosphere came from. They mostly came from outgassing. As the planet cooled, got a solid crust, these were the gases that were released. Various chemical processes, volcanic eruptions, lots of water vapor. And so now we're learning that this secondary atmosphere and those general processes would have applied to all three terrestrial planets Venus, well, not all three, but the three that we're talking about, Venus, Earth, and Mars. Okay. But the final atmosphere is quite different. So although the primary and secondary atmospheres are shared between these three worlds, their current atmospheric compositions depend on the difference between the planets. So over the billions of years since we all three lost our secondary atmospheres, the the difference between our size and temperature has dictated very different atmospheres. What is interesting is that composition-wise, Venus and Mars actually don't look that different. They have very similar compositions. They only differ in the amount. So check it out, right? Venus, 96.5% carbon dioxide. Mars, 95.3. A little bit of nitrogen, a little bit of noble gases, right? More, significantly more on Mars, right? Because noble gas is a tiny percentage over here. And this is closer to Earth's. And sulfur dioxide in a little bit more, actually measurable, where no measurable amount on Mars. Okay. Water, a little bit less on Venus. Both cases, almost no water, although where it went is a very different story, you know? And talking about where the water went is actually a really neat way to compare. I mean, obviously the carbon dioxide sharing aspect is cool too. That you got these two worlds that maintained huge amounts of carbon dioxide. We didn't basically because of life, right? And its ability to lock that in. And the fact that our water became a liquid ocean where it didn't become a liquid ocean for the other worlds, but it didn't do quite the same thing either. And so I won't jump ahead right now, but the water that did exist in this right secondary atmosphere for both Venus and Mars, it went away, but it went away in very different ways, and more literally disappeared than it did for Earth. All right. And it's actually kind of okay, even more than that. What I will hint at is that with Mars, it's potentially still, it's obviously not in the atmosphere anymore, but it's potentially still accessible. Most of it probably is underground, but not like in big lakes or anything in any liquid form, but frozen, okay, and among rock sheets. So you got, so you could probably like if you could heat up Mars, you could get a lot of the water back. And then once you got it back into liquid oceans, then it's great. That's kind of where you want it, right? If you wanted to terraform Mars, as science fiction novels love to talk about. But with Venus, the water is literally gone. It's in space. It got split into the hydrogen and oxygen and just pushed out into space. There's no if you wanted to reintroduce water to Venus, you'd have to bring it from comets or somewhere else in the solar system. It's simply not there, and it's a lot of water that you'd have to reintroduce. So, last couple minutes. Venus has an escape velocity. You're going to see some escape velocity in the next homework I post. I keep hinting at it, which I actually probably will get up today. I sure hope so. And the escape velocity, so this is the speed you need to achieve to get away from the gravitational pull of Venus, is 10.4 kilometers per second, quite comparable to Earth's. All right, this is really similar to how fast you have to be going to escape Earth's gravitational pull. All right. So, which of the secondary atmosphere gases would be expected to escape into space off of Venus? Good question to start thinking about this stuff. So, of all the secondary components, water, sulfur dioxide, nitrogen, noble gas, which of these do you think would be able to escape into space? Ace was on it. Probably just, it helps that they actually literally put the numbers, right? So that V average, what is that? What does V average represent? Anybody know? Because all of them say VAV, and AVE just stands for average. Average velocity? Yeah, yeah. And all I'll add, it's true, is that it's the average thermal velocity. It's how fast, and you're probably thinking that, but it's how fast the molecules are bouncing around because of the heat energy that exists. So these are all the average thermal velocities of these different gases. So no, none of them are going fast enough. None of them will escape into space. So Venus would hold on to all of those constituents of the secondary atmosphere. But then, why did it change, right? If it was able, if none of them escape into space, right? And this underneath the secondary atmosphere table here, we got formed from volcanism, evolved and changed over time. So I like that has that statement because that's kind of how I've been describing it. So formed from volcanism. So think of that outgassing as the cause of the secondary atmosphere for all three of the planets. But we'll have to think about then what if they didn't escape into space, at least not right away, then what did happen to this secondary atmosphere? How did it become the current atmosphere, and why did it become so thick? Okay, so that's where we'll leave it off for today. It's up to you to look into these answers, pick up on the rest of the Venus atmospheric conditions, the evolution of its atmosphere. When you look into Mars, again, because obviously atmosphere is a great comparison point. So make sure to focus on the Martian atmosphere and how it has evolved. Also, make sure to focus on when there was liquid water on Mars. Hint, it was only for the first 500 million years of its existence. And what is the evidence of that liquid water that remains today? That's about it for my advice. But overall, just look at videos and the chapter content. We will kind of again do a summary of this material when we meet on Monday, but I'll make a Canvas quiz due before then so we can include discussing its answers in class. Other than that, I'll see you on Monday. I'll assume that no one will be taking the exam before 10 a.m. on Monday because that'd be, why take it so soon? But if you absolutely wanted to, you could. But otherwise, expect Monday to be, going over a little bit more that could help for test one. All right. So that's it for today. Let's stop.